So we're going to start our study of circular motion. So this is a shift from one-dimensional motion, which is just motion in a line, to two-dimensional motion. And to look at it, we're going to look at it qualitatively first. And so I built this little GeoGebra app. So this is uniform circular motion. And what I mean by uniform is that if you notice, this thing is moving at a constant speed. Now I can change the speed of it up here. I can make it go really fast or really slow. But the idea is that it's moving at a constant speed around this thing. But now we have to think about the velocity of this. So if I show you the velocity, what you can see is that the velocity itself is constantly changing, not in magnitude. Let me stop it. The magnitude is the length of the arrow, but in direction. So it's constantly changing direction. So you can see it went from something like this to something like this. And so since it's changing its velocity, the direction, we're going to have acceleration. And actually, I think that's all we need for that. But that's what we're talking about. So we're going to look at a qualitative change in velocity. And so I have this circle here. We're imagining that this dot's moving around the circle. And we're going to look at three different instances in time, from here to here, here to here, and over here. So just to remember that the average acceleration is the change in velocity over time. And so it would just be the final velocity minus the initial velocity divided by the time. And we're going to have to use vectors to do this qualitatively. So to subtract vectors, remember that we do it tail to tail. So I've already drawn it out. So for an example, if I go from some velocity here to some velocity here, then my change in velocity would be from the initial velocity. So you would start here, and we would just draw a vector over to the other one. So this right here, this vector here, that would be my change in velocity. So you go from initial to final. And when we say tail to tail, what we're saying is that it's the bottom of the arrows. They go together. And then we just go, and that's your change. All right, so let's suppose this is uniform circular motion. So let me write that. Uniform circular motion. So the uniform means constant speed, not velocity, constant speed. So the magnitude of the velocity. And so this thing is moving at constant velocity all around the circle. Now to draw the velocity vectors, what we do is we just draw a tangent to the arc, to the circle. So tangent, I know you know, is a trig function, but it also means that it's perpendicular to the normal. So if I draw a normal through this thing, so here, let me show you. So down here, I'll do it down here. So if I drew a normal to this line, it has to be just at that instant in time, it's the perpendicular. And then the tangent is then perpendicular to that. So it's a line that goes like that. Okay, so what we want is we want the velocity right here. So we just kind of draw a tangent here. That's not very good, but you get the idea. In fact, let me undo that. I'll just use this line tool. We'll get it as close as possible. But the velocity is going to be something like that. And then it comes up here and the velocity has changed directions, but not magnitude. So that would be my new velocity. So this would be the initial velocity, this would be the final velocity. Okay, if I want the average acceleration between these 2 points, that would be the acceleration right at this point, equidistant from each one. What I can do is I can slide this vector down here and redraw it. So let me do that. So it's about, I don't know how close we can get, probably about like that. So this is now this vector. I've just slid it down here. So that's my final velocity. And now we can draw the acceleration vector. So the acceleration here is like this. That would be my acceleration. Okay, makes sense? So I just drew the two vectors and then I moved it down and found the acceleration. And that would be the acceleration at this point right here. So at this point, we would have an acceleration like that. Okay, let's do it again up here. And what we're gonna do is we're gonna get a pattern out of this. I don't need that. So if I go up here, again, it's the same magnitude as before. So we get our two velocities. And then I'm gonna slide this one over. So we get something like that. And then this would be the initial. This would be the final. So my acceleration halfway between these points is going to be like that. And that would be the acceleration. And finally, let's do it just one more. And then I think we can pull out a pattern. So about like that, about like this. I move the final up here. So about like that. And my acceleration would be kind of like this. Okay, I know I got sloppy there at the end, but we're just trying to get a pattern out of this. So that's my acceleration. Notice I put this C in here. You'll learn about that. But what you can see is that the acceleration seems to be pointing towards some point, and it's actually pointing straight towards here, right towards the center of the circle. And so maybe we could say that the acceleration always points to the center, because that's what it appears to be. And this is only for constant speed. So let's go back to our sim. Let's go look at this thing. Where is it? Here. Okay. Because if I run this thing, I can actually show the acceleration at any given point. And there's our acceleration. So let's stop this thing. So what you can see is that this thing does indeed point towards the center right here. And if I run it a little more, stop it, it's still pointed toward the center. And we see, in fact, it's always pointed towards the center. And so it has a special name. It's called centripetal acceleration, but we'll get into that in more detail. The key is that if it's going at constant speed, the acceleration always points towards the center. Always. Stop. If this acceleration was not pointed towards the center, what would happen? So let me scroll down and we can think about what's happening if it's not going towards the center. Sorry, let me get a circle on here. Okay, so let's suppose we have an object which is experiencing, so it's here, it has velocity this direction, but then it has an acceleration that is not towards the center, which would be like that, but rather kind of like this, kind of angled ahead. So if we had acceleration that way, then what that's going to do is it's going to add a little bit, because you see how we have this component this way, so it's going to increase the speed of this. So it's going to change the direction. This one right here would change the direction. That's the part that's making it turn, but it would also be speeding up. So it would be going in a circle and speeding up. Contrarily, if it was this way, it would turn and be slowing down, because you have acceleration against the velocity. So it would be slowing down, going in a circle and slowing down. But for uniform motion, so for this part, this is what we need. The acceleration always points towards the center. And we can find it using vectors. And that's it.